Okay, excellent. So I'm happy to have here Jingfeng Wu. I'm happy we managed arranging a time, even if some people are still here. It's almost winter. Jingfeng is a postdoc in Berkeley, working with Bing Yu and Peter Bartlett after doing his PhD in Johns Hopkins. And mostly know Jingfeng as one of the most, if not the most active member of the collaboration on the foundations of deep learning that we've had running for 5-6 years now. So he's done really nice work on today we talk about implicit regularization and more generally of understanding learning in deep networks. Jingfeng will be here both today and tomorrow, so you can find the time to meet with us.
Thank you so much for having me here and for the kind introduction. So I'll talk about the implicit regularization, specifically gradient descent versus ridge regression, and some results of this kind today. And feel free to ask questions during the talk. So I want to start from the very basic inequality in ML. You can argue it's very loose, it's very conservative, but it teaches us very important lessons nonetheless. So it tells us to minimize the test error. We want to fit our data by minimizing the training error. And at the same time, we want to have a control over the complexity of whatever we learn. So to have a good generalization, we need to achieve two things together. First, we want to have optimization. We want to minimize the training error. And we do this by calling the optimization techniques we know, for example, gradient-based method. And to have generalization, we want to have a control over the complexity. Okay. So how do we achieve this? You can do, there are many techniques to achieve complexity. I'll talk about that. So for both these two aspects of machine learning, there are very interesting modern questions to be asked. For example, for optimization, some of my past work shows that you can do a larger step size that although cause instability, but can accelerate the convergence of gradient descent. Okay. So you observe this in your network. If you do a small step size, classical theory tells you to do a small step size, where you have this green curve, the loss decrease monotonically, but turns out you can overshoot that a lot. And by doing this, you can converge faster. And so this is something, the oscillation is something classical theory doesn't really allow you to do, but turns out you can, it's not only happening in practice, you can also rigorously prove it in logistic regression. And some of you might find this figure very familiar. I presented this, I gave a talk about this, I think 2 years ago at the TTIC. That's pretty much my first paper on this topic. But over the years, we made significant progress afterwards. And just last week, we did a tutorial about this topic at Neurips. So for audience who are interested in this line of work, welcome to check it out. We have a website about this. And I think the tutorial will also be made, the recording will also be made publicly available afterwards. Okay. All right. So today I want to talk about generalization, or specifically, or equivalently, how to control the complexity. Okay. And I will tell you how to get generalization together with optimization. Okay. Those two aspects are connected together. We cannot treat them separately. Okay. So how do we control the complexity? The classical answer is to have an explicit control. For example, you can control the family of your, you can use a less flexible model family with less parameters, then the complexity cannot be too large. The classical VC theory tells you, it's a classical example for this. And you can also use norm as a complexity control. Peter's paper from 90s tells us for validated generalization, the size of the weights, or the norm of the weights, is more important than the number of parameters in the network. So norm is also a way you can use to control the complexity. But what happens in deep learning? People realize that you can often have an implicit control of the complexity via optimization algorithm. Again, I will tell you two examples. First example, early stopping. When you run your gradient descent, you can stop earlier. And when you stop earlier, the parameter norm it doesn't increase that much yet. So through norm regularization, you can argue intuitively that early stopping provides a complexity control. The second example is stochastic averaging. It's really a classical idea. Directly related to the development of SG algorithm. Dates back to 50s-ish. So by doing this averaging, you kind of have this variance reduction effect that can also control the complexity. So just to make this clear, none of these ideas are really new to deep learning. But
what do you mean by stochastic averaging in deep learning?
For example, you average the iterates. There's some, what is it called? EWA, something. And some people argue it help you to converge to a flat minima. But in this sense, it's just reduced variance. Yeah. All right. So as I mentioned, those ideas, early stopping, stochastic averaging, aren't really the new idea to deep learning. But in a sense, it's more like a deep learning rediscovered, or like it's a good example, like tell us we should rethinking the implicit regularization from the optimization algorithm. So now the question is, how good is this implicit regularization? Do we need them at all? And how does this implicit regularization coming from optimization algorithm compare to the explicit control? If we can already achieve what we want through explicit regularization, why we need to understand this implicit regularization? Okay, and so this question I'm aiming to answer through the talk. But before I tell you the result, there are some challenges we need to address. For example, like when we want to study the implicit regularization, we cannot ignore the issue of non-convex optimization, because the implicit regularization is really tied to the optimization algorithm we are looking at. And talking about optimization, in general, people don't really understand how to do non-convex optimization, and this is the first challenge at least. And even if we ignore the issue of non-convex optimization, there are many confounders. Okay, so specifically, how do we isolate the effect of implicit regularization and explicit regularization? Okay, so for implicit regularization, it's kind of easy. You can turn off every other explicit regularization. So whatever you got from the output of the algorithm, the only regularization you have is from the optimization algorithm. Okay, that's fine. But how do we isolate the explicit regularization effect? Okay, note that in practice, even if you add for example, L2 regularization or weight decay to a network, it's still a non-convex optimization algorithm. You cannot really output the argument of that. We don't have that oracle. We don't have the ERM oracle in practice. So we have to run some optimization algorithm to find the minimizer of the regularized empirical risk minimization program. And then here's the issue. Whatever optimization algorithm you choose to use, it always carries some implicit regularization effect. So in practice, I would say it's really, really hard to really isolate the effect of explicit regularization. Okay, so that's why I think this question is really, really it's not easy to study this question through empirical methods, through experiments. So what's the alternative? Maybe the alternative, I don't know if it's alternative if you think about it in that way. Maybe a sidewalk. Okay, a sidewalk to those issues is to consider a simplest setting, or simplest yet still natural setting, where you can explicitly sidewalk all of these challenges. And the test bed I choose is linear regression. it's a convex problem, so I don't have this non-convex optimization issue. The optimization gradient descent is easy for this problem. And it's a convex problem, so when I add a explicit regularization, for example, L2, the minimizer is unique. So there, I don't need any optimization algorithm for me to find this minimizer. So I can perfectly isolate the explicit regularization from implicit regularization. Okay. So in this simplest setting, I'm able to compare implicit regularization with explicit regularization rigorously. Okay. So this is the problem setting I want to look at. Let me give you a taste of our result. So one of our results says the following: for every Gaussian linear regression problem, random design, Gaussian covariance will specify the y for all of such problems. Okay, every sample size. Early sloping is never worse, but sometimes much better than L2 regularization. This comparison is in terms of the test error. So early sloping is a version of implicit regularization. L2 is the classical explicit regularization, and the result tells you implicit regularization dominates explicit regularization. So let me say a bit more about this result. We did the following. So we compare, by early sloping, I really mean early sloping of gradient descent. And L2 regularization is really just a ridge regression from the statistical literature. So we did the following. We compare these two estimators for every linear regression problem instance. Okay. And so this is already very different from the classical literature. We did an instance-wise comparison instead of the worst-case comparison. Okay.
When you train GD, what is your loss function? You don't add explicit regularization?
That's right, without regularization. So I turn off all the explicit regularization, just doing gradient descent, with a proper sloping time. Okay. All right, so we compare these two estimators for every problem instance, not just their worst-case performance. And we also cover the high-dimensional cases where you have more parameters than your sample size. We also compare those two estimators in those situations. And yet still, gradient descent dominates ridge regression. And we not only compare gradient descent with ridge, we also compare gradient descent with online.
So another question. So ridge regression for me is just a form of loss. So what is the optimizer for ridge regression?
Mean of that, arg mean of that.
So ERM for ridge regression objective.
Regular is the ERM. That's pretty sure. Okay. So what I'm gonna tell you is based on this joint work with Peter Bartlett, Jason Lee, Sham Kakadi, and Ping Yu. So let me set up the notation. I have a random design covariance with covariance matrix sigma, and I have a well-specified linear model. True parameter is W star with a unit of ET noise. So I made the noise level to be a unit without loss of generality. I can always normalize the quantities. And the only assumption here is that I want the signal to noise ratio to be upper bounded by some absolute constant. So this assumption is just to ensure that my problem is noisy. Okay. Otherwise, it could be like a no noise problem. There is I don't want to consider that. So, but this condition I'll only use it once. You will see where I use it. Not you have.
I mean, once you put that, then saying that the noise is magnitude 1, why is that without loss of generality? Or
you can rescale. You can replace 1 by a small sigma square, and you rescale everything.
Yeah, but then you have to replace that 1. I mean, you have 2 1s there, right? I mean, I can make. I can
Yeah,
see why one of them can be away.
Both be sigma square, small sigma square. So it's saying the signal is no more than constant times the noise. That's it.
Okay, I see. So in the regime, you're in like a high noise
Noisy
regime.
it's not high noise, just a constant noise.
Okay, fine.
But you will see I'll only use this
I
condition
understand.
once.
Good. Okay.
So All right. And each problem, each linear regression problem is determined by the covariance sigma and the true parameter W star. Okay. So I'll measure the performance by the excess risk or prediction error, which is just the mean squared error between your estimator and the true parameter W star. And I'm in the classical non-asymptotic setting. I have n samples, ID from the population distribution. Capital Y, capital X is a collection of those of my data. This is all the notation I need. So here is the estimator I'm comparing. Ridge regression is the minimizer of the L2 regular is the empirical risk minimizer objective. It has an explicit formula, so no optimization involved. Explicit regularization. And here is a hyperparameter lambda. It determines the strength of the regularization. Okay? And I'm requiring the regularization to be non-positive, non-negative. And gradient descent is defined as following. Starting from zero initialization, because I want to compare with ridge. Otherwise, you can, if your initialization is not zero, you should center the ridge regularization from the other parameter. Okay, so it takes t steps of gradient descent with step size eta. The step size is not so important. You can think about gradient flow without affecting the final answer, but I do want to cover the finite step size situation. So the output is the last iteration of gradient descent. Okay, the main hyperparameter for gradient descent is the stopping time t. The number of steps you do. So now I want to compare the test error or the excess risk between this.
Sorry, the step size doesn't need to depend on the lambda max?
That's the only condition, yeah. As long as you are satisfying the descent lemma.
Yeah.
It needs to satisfy the descent lemma, but it can be arbitrarily small. You just rescale the solving time.
Oh, I see. So what is the what's the eta in your analysis?
It's 2 over the maximum eigenvalue of the empirical covariance.
Empirical covariance. Okay. Thank you.
All right. So what I'm gonna do is compare the excess risk between these two estimators. Okay. So I've already told you. Told you that the GD error will be no worse than the ridge error. Okay. To prove this, I need two things. I need an upper bound for GD, and I need a lower bound for ridge. Okay. So that's what I'm gonna show you next. But before I do that, let me introduce a couple of more notations. Okay. So sigma is the covariance of the of X. The lambda IUI is singular value decompensation in non-increasing order, and for a index k, sigma 0 to k denotes the head component of the covariance, and sigma k to infinity is the tail part of the covariance matrix. And PSD matrix M, the inverse is always pseudo inverse, and the matrix norm of vector is a quadratic form. It's following quadratic form. Okay. It's fine to ignore those notations. You can just compare the upper bound and lower bound. I'm going to show you next. Okay. So remember, I need a lower bound for ridge and an upper bound for GD. Luckily, the lower bound for ridge is already done in the literature from this paper by Alex Ziegler and Peter Bartlett, Binary fitting ridge regression. There are other papers providing similar bound in around the similar time, but let's use this one as an example. So, okay, quite complicated formula on the expected excess risk on ridge, but let me break it down for you. So there's a critical index k star, divides your space into a head component and a tail component, and then after you do that, you have this notion of effective regularization, and then this effective regularization leads to this effective dimension. After you, with these three definitions, the bound is really like a bias error plus a variance error. Okay, the bias error involves W star, the variance error. You can think about it as a contribution of the unit additive noise. Okay. So, and by the way, if you are in the classical finite dimensional setting, this bound recovers the classical well-known bound, DON bound. Okay. All right. So a couple of more notes regarding this bound. First of all, I'm ignoring a numerical constant here. Okay. But it's possible to get the constant correct using random matrix theory tools. There are some nice works in the literature doing this, but I'm not doing it today. So all of my comparison will be up to a numerical constant. Okay. But the constant is numerical. It doesn't depend on anything. Okay. And this expectation, you can replace the expectation lower bound by a high probability lower bound. It's also doable. So the same, the right-hand side is also an upper bound with high probability for the risk of ridge. Okay. So the right-hand side is really tightly characterize the real behavior of ridge regression for each probability.
So my question is about the asymptotic thing. So in what sense is this? So this is, you write it as an asymptotic lower bound?
It's a finite sample lower bound.
Oh, it is finite sample.
Yeah, non-asymptotic.
Okay.
For every sample size, this is true. The numerical constant.
So why did you? Okay, so that just means that greater or equal to squiggly?
Oh, it's ignoring a numerical constant.
Just ignoring a numerical constant.
Correct.
But it is true
for every
sample size. Every sample size, both the upper bound and lower bound.
That's right. Yes. So yeah, it's non-asymptotic one. And all right. So this lower bound from this paper by Alex Sigler, Peter Bartlett, it tells us a lower bound on ridge. So what we did in the paper is we prove a comparable upper bound for gradient descent. Okay. So here's what we proved. For every step size beta no larger than 1 over trace sigma, it's really just the 2 over the empirical eigenvalue of the empirical hashing. But in the paper we wrote it this way, but this is a sufficient condition for that. Okay. And for every sample size, for every sloping time, we have this upper bound. Critical index, effective regularization, and effective dimension. Those definitions are very, very similar to what I showed you in the last slides. And then the bound also consists of a bias error and a variance error. So the bound looks really comparable to what I showed you for ridge, just the two differences. Okay. The first difference is that the variance error here is DON, but it was mean of DON and 1 before for ridge. And then the regularization, for ridge it was lambda, but here for gradient descent, the lambda was replaced to 1 over eta t here. Okay. That's the only two differences. And now I can give you a proof why gradient descent is never worse than ridge. The proof is just the one line. If the effective dimension is greater than your sample size, you don't do anything. Okay, that's why I need so Nati here is where I use the finite noise, signal to noise ratio condition, because I want to compare garbage with garbage. If d greater than n, then I'm not doing anything, and the GD is garbage, but ridge is garbage either. So otherwise, meaning that the ridge is learning something. Ridge has a non-trivial test error. In this case, I just matching t with we just matching this one way that t with lambda. Then my upper bound perfectly matches the lower bound for ridge. That's a proof. So all the heavy lifting are in this upper bound proof for GD. But once you have that, you immediately see why GD is no worse than ridge.
And also ridge no worse than. Wait, it's a bit confused. I mean, didn't you just show us that they're the same?
No, this is just an upper bound for GD. The upper bound could be loose.
Okay. I see. So for ridge it's tight, and for GD it's just an upper bound.
It's not tight.
I see. Okay.
Good question. So So for ridge, this upper bound is tight, but for GD, this is just an upper bound. And I will show you why this upper bound could be loose. Okay. So this theorem, I'm summarizing what I told you so far. For every Gaussian linear regression problem, remind you the definition here. For every sample size, for every hyperparameter for ridge, okay, there exists a stopping time for GD such that with hyperprobability, the GD error is no worse than the ridge error by a numerical constant. And this stopping time is actually has an explicit formula. It's either 0 or 1/8 number. And so this is what we proved in the paper. So the most relevant prior work tells us the following. Assuming you have an isotropic prior on the true parameter, they are in the basin setting. And then this paper by Ali Coiter and Ryan Kipshrani, they show that the access risk for GD is no more than 1.69 times the access risk of ridge. Okay. So our numerical constant is greater than 1.69, but we don't really need this isotropic prior. Okay. And on the other hand side, I would say this prior work is actually very misleading in the sense that when you have an isotropic prior, ridge is base optimal. No other estimator can beat ridge in terms of the actual error. So taking into account of the numerical constant, no other estimator can beat ridge. So what they actually show in the paper is the following. If you tune those two algorithms optimally, they are the same up to a numerical constant, 1.69. Okay? GD is no worse than ridge, but optimal ridge is no worse than GD either. So their result shows when you have a isotropic prior, those two estimators are the same. But actually, gradient descent can be much better than ridge. I'm gonna show you next. Please.
What's the intuition about when we are in isotropic, they are quite similar, but when you have and the covariance has the weird directions?
It doesn't need to be weird. It's a very natural case. GD is already
no,
better.
Just do you have any intuition about, for example, my understanding is that you're saying that in isotropic case, they are roughly the same, up to 1.69.
Exactly, yes.
What is the reason that when we go beyond isotropic, they look different?
First of all, there's no reason to believe they look the same in general. It's a two different estimator. And but more technically, the reason is because ridge put the same regularization in every direction. When your covariance is isotropic, you don't need to distinguish them. So you can put the same regularization in every direction. But when your covariance has some decay, you shouldn't put the same regularization in every direction. There are some important directions, there are some unimportant directions. So the regularization should be more adaptive to the strength of your covariance. And GD exactly does this.
So I don't know. Just a simple.
Are you going to show this?
Yes.
Yeah. So maybe we'll wait until. Yeah.
But why can't you control lambda if lambda is not fixed? If lambda would be adaptive, wouldn't it solve the problem?
That's not rich. You are saying replacing L2 by some matrix norm regularization. You need to know the oracle information. You need to know the signal. You need to know the coordinate system.
Okay, but it's not ridge anyway. That's what you're saying.
You can say it's a generalized ridge, but it requires oracle information.
Just to so maybe we'll let him continue. I think just to clarify, you're talking about changing a scalar lambda, or
yes.
No, that's not going to help.
A scalar lambda
is
not going to help. But you need to do a matrix hyperparameter.
Okay, but maybe we'll continue and then it'll become
okay. Yes. But just to, I'm comparing, this is a fair comparison, right? There's a scalar hyperparameter for ridge, and there's a scalar hyperparameter for GD. I'm not cheating in any way. Okay. So here's an example where GD can be much better than ridge. The example is very natural. I would say it's not weird at all. So the power law class, the covariance decays according to some power law with a exponent a, and then when you project your parameter in the coordinate system of the covariance, it also decays at some power with exponent b. Okay. A and b greater than 1 to ensure the trace is summable, the signal is also summable.
What's UI is the
UIs are the eigenvalues.
Yeah. Eigenvectors.
Eigenvectors.
Okay.
Right. So in the literature, you might have heard the words like a source condition, capacity condition. It refers basically the power law class. Okay. So and this subclass of the problem, there are only two parameters, A and B. So you can really brute force the rate for all the estimators. And I'm showing you a table for the rate for all of the estimators. Don't look at those rates. It's a bit take some time to phrase, but I have a plot in the next slides show you this comparison. But if you stare at these numbers for 5 minutes, you will figure it out that GD is always minimax optimal for this subset of problem. And ridge or SGD, I'm gonna tell you next. Ridge and SGD could be polynomially suboptimal. Okay, for this subclass of problems. Okay, let me give you a plot for what I'm showing. Here I'm fixing this source exponent A and varying the capacity exponent B. Okay, and I'm plotting the exponents of 1 over n for each estimators. So the bigger the better. The bigger it decays faster. Okay. So the minimax rate, the exponent for the minimax bound and for gradient descent, they perfectly match, meaning that G is always minimax optimal. For ridge, it can be suboptimal when B is very large. Okay. And you get the wrong exponent, so it's polynomially worse even. For SGD, it's also, I haven't told you SGD yet, but I will give you a definition later. But SGD is also polynomially suboptimal when B is very small. Okay, so none of these two estimators are optimal, but they are suboptimal in different regimes. And it's interesting to observe that if you take the best of ridge and SGD, this is minimax optimal.
What about SGD on the regularized loss?
Where is
SGD? What about if we do SGD on the regularized loss? Is that also optimal?
Good question. I think it's likely. Yeah, you can tune it. Oh no! It doesn't solve the ridge because it's online. It doesn't solve the ridge.
It doesn't.
I don't think it's gonna be optimal. But yeah, I need to check the math. But intuitively, I don't because it doesn't really solve the ridge.
So just to understand here again, so you're saying that ridge actually is suboptimal for very easy problems, correct? And SGD is optimal for hard problems. Is that the correct?
Hard and easy depends on the algorithm. I would say ridge is so it's easy for optimization.
No, but it's also you need less, isn't it? Just hard and easy in terms of like how many samples you need or what error you're going to get.
Oh, I see. Yeah, exactly. Yeah. So ridge is over-regularized in those cases. So you don't need that many. There are just a couple of like. So basically, when B is very large, the signal decays very fast. It's basically like a sparse problem. You don't need a regularization in every direction. So and ridge put the equal amount of regularization in every direction. It's overly regularized. And right, so even in this power law class, very natural power law class, you can already see like GD and ridge they are not equivalent. Okay. And know that because of this decay is not as trivial, so it's not contradicting with the prior work either. So all right, let me summarize what I told you so far. So I've showed you that in terms of test error or sample complexity, gradient descent dominates ridge in the following sense. For every linear regression problem instance, GD is never worse, but it could be much polynomially better than ridge. And I have one remark about the computation. Although I'm talking about the full batch gradient descent, you can make a mini batch version and still work out. The theory will still work out. So specifically, the mini batch version, I'm calling this algorithm multi-pass SGD, just to distinguish with the SGD I'm gonna show you next. So by multi-pass SGD, I mean sampling a mini batch with replacement from your empirical data. Okay? If you do this, the computational it's kind of light, and this algorithm, the test error of this algorithm is never better than gradient descent. The reason is very simple. Because when you take an expectation over the sampling, the expectation is exactly gradient descent because this is a linear problem. Okay, and the test error is a quadratic function of your estimator. So, and I have the same. This estimator is unbiased of that thing, only considering the error of the randomness of sampling, and so I'm gonna pick up an additional variance. Okay. That's why multipass SG is never better than G. Okay. However, if you do the correct step-size scheduler, this estimator you can make the error arbitrarily close to G. So in terms of the statistical performance, these two estimators are the same. These two algorithms are the same.
But you also didn't win. But then you also didn't.
You didn't win. Yeah, I'm
you
saying.
didn't win in terms of computation either.
You win in terms of
you do win?
because each iteration you only draw one sample.
Yeah, but how many passes do you need?
Same amount of passes. Log many.
Okay.
Yeah. Because the step-size scheduler you need.
Okay.
But if you do, yeah, it's so yeah. All I want to say is like the computation issue of gradient descent. You can solve it with a classical ideas. Okay. All right. So I also want to show you. I also want to discuss a little bit why this result looks so simple, so classical. Why we don't know it earlier. Like linear regression, people have been studying linear regression probably for 200 years or even more, even longer. But we don't. And gradient descent is not a new idea either. Why we don't have this observation much earlier? It turns out it's very fun. And you shouldn't expect we know this before because of the following reason. Okay, so fixed design is very easy. If the design matrix X is fixed, you only have randomness from the label. This case is very easy. And indeed, this paper by Helen Foster Kakadi and Sham Kakadi is also one of my collaborators. So their paper in 2013 already tells you a result similar to ours in the fixed design situation. Okay, so specifically they show that PCR, if you're doing a PCA and doing ordinary least squares together with PCA, this estimator is no worse than ridge regression by a factor of 4. However, going from fixed design to random design, their paper is surprisingly short, just 6 pages, including experiments. 6 pages paper in 2013. It's very hard to imagine nowadays a theory paper can be only 6 pages long. By the way, I also learned this risk comparison idea from Sham and indirectly from this early paper. Okay. That's one of the motivations why I want to compare the estimator in the instance-wise. But when you go from fixed design to random design, this becomes very, very different. Okay, I will tell you so why it's very different. So first of all, I want to do it in instance-wise, not worst case. Worst case is easy to analyze even when random design, but it becomes significantly harder when you want to go to the instance-wise. And high-dimensional case, and the second reason I think it's most important reason is that in the high-dimensional situation, random design and fixed design are significantly different. There are very surprising phenomena in the high-dimensional random design setting. For example, this pretty famous paper by Peter Bartlett and other co-authors on benign overfitting. You don't see benign overfitting in fixed design, but when you're in a random design high-dimensional setting, there are surprising phenomena like benign overfitting, among others. And Peter's paper on benign overfitting is 44 pages, significantly longer than the fixed design one. And our result you can it's built up on the benign overfitting line of work. So I would say the right tools to get this result only appears in 2019 or afterwards. So you don't really, without understanding this high-dimensional phenomenon really well, it feels hopeless to have this dominance result before that.
So the 2013 paper, that wasn't explicitly about gradient descent.
It's not about gradient descent.
Right,
it's another estimator dominance ridge.
Yeah.
It's not about gradient descent. But to be honest, it's not hard to work out gradient.
Yeah, because it's basically mimicking what gradient descent does.
In fixed design, yes. In random design, it's unclear. Yes. Right. So, okay. So, I'll tell you more surprising results about gradient descent versus online SGD. Okay. I've already told you gradient descent dominates ridge, but how about gradient descent compared with other estimators, such as online SGD? So I'm giving, let me define the estimators first. Gradient descent, same as before. Hyperparameter is the stopping time. And I'm comparing gradient descent with the online SGD. Or SGD, I'm considering this variant of SGD, but there are other variants in the literature as well. You can extend the discussion to there as well. But let me focus on this one. Same initialization 0. Step size, initial step size eta. And I'm doing a step size decay scheduler. Every capital N number of steps, I'm going to decay my step size by a factor of 10. Okay? And then the output is the last iterate of SGD. Each sample is only used once. So alternatively, you can consider constant step size with iterate averaging or tail averaging. The discussion will hold as well for those variants of SGD. I picked this one for the discussion because I think this variant of SGD is most close to what people do in reality. And because each sample is used and only used once, there's no solving time is no longer a hyperparameter we are able to tune. So the only hyperparameter here is the step size, eta. Okay. For stability, the step size cannot be greater than some constant over the trace. Otherwise, the stochastic process cannot converge. So what I'm really actually doing here is I'm comparing the implicit regularization. I'm comparing two different sources of implicit regularization. One from a batch optimization algorithm, the other from an online optimization algorithm. I'm comparing zero regularization effects, similar as before. So to do this, I need to have a bound on SGD. And luckily, this is done in my PhD work. So in my some of my PhD work, we prove the following. For every step size, in expectation, you can calculate the expected risk for SGD. Again, looks very similar to what I showed you earlier. We have a bias arrow, we have a variance arrow, but now the variance arrow is similar, but the bias arrow decays in a geometric fashion. Okay, this is a bit different from the ridge lower bound and the GD upper bound I showed you earlier. Effective steps, capital N, because I'm doing this step size scheduler. Critical index, effective dimension. So, right, this capital N, you can make it a small n by doing tail averaging instead. So that's even if you don't do that, it's just a log factor. So now let's not worry too much about that. And this 1 over eta n, it was the effective regularization, if you remember, in the definition for the ridge. Okay, but here it's replaced by this 1 over eta n factor. It's a matching upper and lower bound up to a numerical constant. So in the finite sample, non-symptotic, so the right-hand side faithfully reflects the actual error incurred by SGD. Okay. Now, I'm asking the question, how would the gradient descent compare with SGD? Okay. Before we do that, let's first compare SGD with ridge, because we have the type bound for ridge.
I'm a bit confused. So this is fixed step size or varying step? I mean, is this with the varying step size from the previous?
So eta is the initial step size.
So this is with the this is specifically to the
step size
the schedule from the previous slide. Okay.
But you can prove similar bound for tail averaging constant step size, similar variance. And it won't change the discussion. Okay. It won't change the conclusion. Okay. All right, I've told you one upper bound for GD, the tight bound for ridge, and tight bound for SGD. And I want to compare GD with SGD. So before we do that, let's first review how SGD compares with ridge. Okay. We already know those algorithms doesn't dominate with each other because there are some cases where SGD is polynomially worse. There are also cases where ridge is polynomial worse. So it's clear those two estimators doesn't dominate each other. But how about in a more general instance-wise setting? Let me list. Let me give you a table for their bounds. Take some time to phrase, but let's not doing that for now. Just want to point out a couple of key differences. Okay. So first of all, their access rates all follow in the same template. Bias plus the variance. The variance is some effective dimension over the sample size. But here are a couple of key differences. So first of all, the bias for SG, it decays faster than ridge. Okay? Because it really decays in this exponential manner in the hash space. But ridge, you only have this number to the square. It feels like a polynomial rate. Okay? Instead, SGD has this geometric rate in the bias error. And on the other hand side, the regularization SGD gonna provide, there's an upper bound for that. Because my step size cannot be, there's a lower bound for that, sorry. You cannot create a very large, or you cannot create a very small regularization because my step size cannot be too large. Otherwise, the process cannot converge. Because of this constraint on the step size, this effective regularization for SGD, it cannot be too small. And similarly, this effective regularization for ridge, you have this second term contributed from the sum of the tail. So suppose that your tail is very heavy, then there is an implicit lower bound for the effective regularization for ridge as well. So those are the three key differences. Okay. Now remember, I told you an upper bound for GD that beats beats ridge. Now here's the question: would you say the GD behavior is closer to SGD or is closer to ridge? What's your guess?
You told us already, so. Mm-hmm. You told us already, no?
So what's your answer?
That yes, it's going to dominate, no?
It's going to dominate ridge, but would you say it's dominate SGD as well?
I think you showed that yes, in some sense, yes. No?
In the power law case, yes, but it's just a special subclass of the all linear regression problem. So remember, the big difference is that SGD has this geometric behavior in the bias error. Ridge doesn't have this. Would you say gradient descent have this behavior or not? So very surprisingly, GD doesn't dominate SGD. Although it dominates in this subclass, it doesn't dominate SGD in general. Okay. Here's a counterexample. It takes me a very long time. In this project, to figure out this counterexample takes me the most of the efforts. So I find it very surprising. But it also it makes a lot of sense intuitively. So here's an example. I have to be in a very high dimensional setting where the dimension has to be greater than sample size squared. Remember, all of this bound I told you, it's asymptotic. It's non-asymptotic. The dimension and sample size are decoupled. So those bound allows me to consider a sequence of problems where the dimension grows with the sample size. Okay, that's why I'm considering, that's why I'm constructing a sequence of problems as a function of the sample size. Okay. So W star only have a signal in the first direction. Sigma has one large eigenvalue in the first direction, but has a bunch of very tiny eigenvalues in the tail. And D is greater than N squared. That's important. Okay. For this problem, you can verify that we satisfy this finite signal to noise ratio condition. And you can work out the rate for gradient descent and SGD. So for gradient descent, however you tune the step size and the stopping time, your error will be at least N to the minus 0.2. This 0.2 number is pretty arbitrary. You can tune the 0.9 to make this arbitrarily close to 0. And for SGD, if you do a constant step size, you can get an error no more than log n over n. There's a polynomial separation between SGD and G. So combining this with a power law class result, it tells you there are cases where GD is polynomially better than SGD and vice versa. So those two estimators doesn't dominate each other. And in terms of implicit regularization, it really tells us in a high-dimensional situation, online learning can actually be polynomially more efficient than the batch gradient methods. Okay, so it may sounds very weird. This example may sound very pathological to you. I have a better explanation why SGD can be better than G. So here is a lower bound we proved for gradient descent. Okay, here's a lower bound we proved for gradient descent. Similar template as before. We have a bias arrow, we have a variance arrow. Effective dimension, the variance arrow is really similar to the ridge one, but the bias arrow, here's the interesting part. Okay, the index, the critical index, is not K star anymore. Instead, it's something I call benign overfitting index. So it's really the critical index for ordinary least squares or ridge regression with lambda equal to 0. Okay, and so the lower bound tells you two things. The variance arrow for gradient descent is in the same scale as the variance arrow of the corresponding ridge where you match lambda with 1 over AFT. But the bias arrow of gradient descent is at least the amount of the bias arrow of ordinary least squares. Okay. Now, here's something very interesting. In finite dimensional case, OLS bias is always 0. That's a classical understanding. But in high dimensional case, OLS could incur a large bias arrow. Okay. That's why gradient descent could be bad in high dimension compared to SGD. Remember, for SGD, the bias arrow decays geometrically, but here, the lower bound shows that cannot be true for gradient descent. There is a polynomial barrier for gradient descent. Now the question, when would gradient descent dominate SGD? It turns out it will dominate SGD for significant subclass. And to do that, we show the following upper bound for gradient descent. The upper bound it's better than, it's incomparable with the ridge bound, with the first upper bound I told you for gradient descent to beat the ridge. And it's faster, but it only applies to a very early stopping time. Specifically, the stopping time has to be no greater than the sample size n. Okay, so it's also true for online SGD. The stopping time is always n in a sense because it's online. So we have a geometrically decayed bias arrow. We have the variance arrow. Those two terms are matching the SGD one, but the issue is I paid the third term, the d1 over n squared. Here's the definition of those critical quantities: critical index, effective dimension, and the order 1 effective dimension. The first two terms match the actual behavior of SGD, but the GD could be bad because of the third term. Okay, so the first two terms is same as SGD when you imagine the stopping time as the sample size. The issue comes from the third term. So specifically, the effective dimension D is never greater than the order 1 effective dimension D1. But there are some hard examples. For example, the one I showed you earlier. For those hard examples where the order 1 effective dimension could be much, much larger than the effective dimension. Those are the cases where gradient descent could be much worse than SGD. And because of the lower bound, this order 1 effective dimension is not an artifact of the analyze. It also appears in the lower bound. So this is not an artifact. The rate, the exponent 2 might be improvable, but the appearance of the d1 somewhere in the bound is necessary. Okay. And this upper bound also give us insights where gradient descent would dominate SGD. Specifically, as long as d1 is not much larger than d, for all of these cases, gradient descent would dominate SGD. Because of this, then this upper bound completely matches the lower bound for SGD. And turns out there is a very natural condition for d1 not much larger than d. The following condition: it requires the spectrum to decay fast and continuously. Okay. For the sake of time, let me show you the critical examples for this condition. So this condition is satisfied if your spectrum decays geometrically or polynomially. This includes the power law class or the source and capacity conditions. And it's violated if you are in the benign or fitting regime. The third example where you violate this condition is exactly the condition where you have benign or fitting, where the spectrum decays super slow. All this spectrum I showed you in the hard example It decays very fast because D could be very large, but it decays in a non-continuous way. So intuitively, this condition rules out binary fitting. But it also ensures D1 is no larger than D by a numerical constant. With that, I can summarize the final theorem I want to tell you. For all of the Gaussian linear regression problem, satisfying this condition that requires spectrum to decay fast and continuously, GD dominates SG. And the proof is one-liner, given the result I told you already. And specifically, I want to emphasize that this condition is only about the spectrum. Has nothing to do with the signal distribution W star. So in a sense, if you are in the kernel setting, if you know your kernel satisfies this assumption, then it's safe to use gradient descent instead of SG. All right. So let me summarize. I started with the most general set of problems, all noisy Gaussian linear regression. In all of these problems, GD dominates rich, but it's incomparable with online SG. And once you have this fast and continuously decay spectrum, GD starts to dominate online SG. And for the subset of this subset, where the spectrum and the signal satisfying the power law decay condition, there is a regime where ridge is optimal. There is also another regime, SGD is optimal, but GD is minimax optimal for all of these poles. And if I have to put the binary fitting into the picture, it will belong the biggest set. So that's all I want to tell you.
So what you say about GD is equivalent to multipass SGD, basically?
That's right. Sample with replacement. That's crucial. So maybe I can use the time to discuss one open problem. I find it very interesting and subtle. It's about how to reuse your data. If you do, so I've told you SGD, gradient descent and online SGD are incomparable. And I've also told you multipass SGD, or like Z mini-batch SGD with sample with replacement. These are basically equivalent to SGD, to gradient descent. But turns out if you consider sample without a replacement, it's gonna dominate everything I told you today. Okay. So specifically, it means you only start to reuse your data after you run out of this epoch. Okay. It will dominate both because the first epoch is exactly recovers SG. Okay. And if you took the step size go to 0, it recovers gradient flow. So that's why multi-epoch SG will dominate gradient descent SGD, and therefore it also dominates ridge. That's the best estimator.
How many? Okay. I'm confused. But how many passes?
The computation is inefficient, and that's why. Okay. So the question is, were you taking into consideration of the computation? These are the trivial answers where you can beat this estimator. But what's the actual effect of multi-epoch SG? I don't really understand it, and that's the open question I want to ask.
Okay. So actually, I have some questions exactly about this. So one is about the computation. So in all these, so the GD, you have to have a linear number of steps. So, I mean, T is going to
could be polynomial in some way.
It can be polynomial, right? But yeah, but not for multipass SGD. That's a logarithmic. That's
just at most the log many overlap, log times overlap compared to GD at most.
So the real difference here is one pass versus log passes. Between you comparing SGD?
I think it's reuse data, whether you sample with replacement or without replacement. These are the key differences.
I see. And then, okay, so then you have two parameters here, eta and the step size and
correct.
Stopping
so
time.
It's cheating, kind of. You have more hyperparameter to two. That's right. You have epoch number and step size to two here. But it's like in the extreme case where the step size is significantly suboptimal, you recover gradient descent. In another extreme case where the epoch number is significantly suboptimal, you recover SGD. But in its most generic formula, we have a non-trivial epoch number, non-trivial step size. What's the actual performance of multi-epoch SGD? I still don't understand. And because the correlation comes into the play in a very funny way, I don't really have a very good idea how to analyze this behavior.
So how do we? effectively, how do we choose either the ridge parameter or tau and eta? I mean, can we do this in a computationally efficient way?
You can do it by cross-validation research.
Okay, but that's not going to be computationally efficient.
Why you say it's computationally efficient? I think it's just a log many. It's log many trials. It's probably so. If you know a lot about alpha. And I would add that tuning the solving time for GD is not harder than tuning the hyperparameter for ridge, because we have an explicit formula for ridge to beat ridge. For GD to beat ridge.
Yeah, I'm more worried about tuning the step size.
For GD, it doesn't matter. For multi-epoch, actually, I don't know.
Other questions? Okay, let's think again.